Howdy. I wanted to do problem number 22 from page 489. Because it gives us a couple of interesting insights. In this problem, we have 2 point charges that are placed 5 centimeters apart on the x-axis. Now, the problem doesn't tell us which one is placed where, so just arbitrarily, I'm going to place the 3 microcoulomb charge here, and the negative 2 microcoulomb charge right here. And I'll label this as x equals 0, and this is x equals 5 centimeters. And now they ask this question. A, at what point or points is the electric field equal to 0 along the axis? So we consider why that might be so. You can see that the 3 microcoulomb charge is going to produce field coming out of it like this. And you can see that the negative 2 will produce field going into itself like this. And so you can imagine that maybe, just maybe, there might be a point out over here to the left, or perhaps a point out over here to the right, where the field is 0. Notice that it's physically impossible for the field to be 0 between 0 and 5. This X is meant to indicate impossibility here, so let's do it like that. Not going to happen, because the 3 microcoulomb is producing field to the right, and so is the negative 2 microcoulomb, and when I add up field to the right and field to the right, I'm going to get field to the right. So, I don't know where this point is, or points, and so I'm going to just pick a location, and I'm going to call it X. And when I pick that location and call it X, I'm going to compute the total field, which is going to be the contribution from the 3 microcoulomb and the contribution from the negative 2 microcoulomb. And so here we go. The field from the 3 microcoulomb is going to have a value of K times 3 microcoulombs all over the distance squared. Now the distance is going to be the distance from X to 0, and that's just X. The direction of this field is negative because the field is coming out of the 3 microcoulomb and pointing to the left at point X. Meanwhile, from the negative 2 microcoulomb, we have a field of K times 2 microcoulombs all over the distance, and here the distance is the distance from X to 5 centimeters, which is going to be X plus 5 squared. And because the negative 2 microcoulomb charge is negative, then the field contribution from it is going to pull to the right. So this gives me a plus. And all of this field now is supposed to add up to 0. Well, there's a couple ways that I could solve this, but I kind of like simplifying first. I'm going to divide both sides by K, and I'm going to divide both sides by 10 to the 6th, so that I get a greatly simplified equation. Which looks like this. How to solve this? Well, again, I could resort to calculator, but I think some algebra can work. If I add 3 over x squared to both sides, then I get a relatively friendly equation that looks like so. And maybe I can do a little bit of cross multiplying. And now I can take a square root of both sides, so that I get x times root 2 equals x plus 5 times root 3. Now, because I took a square root, I have to take into account the possibility that either I have plus or minus square root here. So this gives me 2 different equations. The square root of 2 is 1.41. The square root of 3 is 1.732.
Chap, date.
So this is my first equation with the positive root, and this is my second equation with the negative root. And when I solve the first equation, I get 1.41x equals 1.73x plus, calculator gives me 5 times 1.73 is 8.65. And subtracting 1.73x from both sides, I get negative 0.32x equals 8.65. Move this down a little bit. Or in other words, x is equal to 8.65 divided by negative 0.32, or negative 27 centimeters. So our first point where we have zero field is way out over here at negative 27 centimeters. Second place where we have zero field is found by solving this equation. Minus 8.65. And so when I solve here, then I get 3.14x equals negative 8.65. And x is equal to negative 2.75 centimeters. And this point is much closer to the positive 3 microcoulomb charge. I'm sorry, I mislabeled that just a little bit. Should be negative 2.75 centimeters. So we have 2 points where our field is equal to 0. And if you were to look at a graph of field, that graph of the field, the magnitude of the field, as a function of x is going to look something like this. It's going to blow up here, and also let's see. The magnitude of the field is going to be infinite right at 0. It's going to come down and hit right here at negative 2.75. And then it blows up again at 5. And then it comes down and it gradually hits 0 and then kind of bounces off and hits towards 0 again. Just like that. So there's our field. What about part B? In part B, they ask us for the points where the electric potential is 0. And this is a much easier problem because we don't have to worry about direction, and also because we don't end up with a quadratic. The total potential is simply the sums of all the potentials at any point x. So again, if I pick, remember that I've got a 0 and 5, and I have a 3 microcoulomb charge here and a negative 2 microcoulomb charge here. And so if I pick some point x, then the total potential is simply kq over r. And so the total is going to be equal to 3 microcoulombs times k over the distance x minus 2 microcoulombs times k over the distance x plus 5. And all of that has to equal 0. We're going to use a similar algebraic strategy here. We're going to add 2k over x plus 5 to both sides. divide both sides by k, and cross multiply. And this is a much, much easier equation to deal with, and it also only has one solution. So when I subtract 2x from both sides, and I subtract 15 from both sides, I get x equals negative 15 as the point where we have zero potential right out here. Notice that that was a much simpler computation than for the electric field, which we kind of expected. Now the question is, what is the relationship between all of these? Well, if I sketch a graph of the potential as a function of x, let me take a moment to do that. Go ahead and pull up a calculator here. Not that calculator. Graphing calculator. Do I have one? I should somewhere. There we go. Let's see if we can get our graphing calculator to pay attention to us. Okay, so here's what I wanted to show you. And that is that we have a graph of the potential in red. That's our y2, 3 over x minus 2 over 5 plus x. And I've left out the k and the micro just to scale things. And if we trace along right here to the point negative 2.75, and you can see, that didn't work. Try this again. Trace. There we go. To the point negative 2.75. And you can see that right here, the field is zero, just as we predicted. And the voltage, the electric potential, is at a maximum point. In other words, the field is going to be zero when the voltage takes on its maximum. We can also see that the field is zero when the voltage takes on its minimum. But to do that, I need to change our window size to see it a little better. Let me change our y's so that we are going from negative 0.1 to 0.1. Graph this again. Here comes the electric field. Notice that it blows up at 0 and also at 5. And here comes my potential. This is that portion of the graph that looked so flat in the previous graph. And when I now hit trace and go to negative 27, you can see that the field is again 0. It's negative 1.7 times 10 to the minus 10. And my voltage is at its minimum, just like that. So that's the thing that I wanted to communicate to you, and that is that the relationship between field and voltage is this, that when the field is 0, the voltage is going to be at a maximum or minimum. I hope this was insightful to you. Take care.